All right, well, good evening. Let's go ahead and just start with what we are doing today. So yesterday we left off right here when we were talking about parent functions. So the parent function is like the most basic form of that kind of graph. So in this case here, we're using an absolute value function, and this is the most basic one there is. It has a slope of 1. It has no x values and no y values. So it's basically just going right through the middle. So parent functions help us kind of think, they help us kind of see where the graph has moved to, because transformations are usually moving a figure or they are changing the shape of it, the shape or size of it. So that's what we're doing today. And again, it's just continuing on with what we were doing the other day. So the objective is still the same, looking at parent functions and describing characteristics of the graphs, and then using those to perform transformations. Now for this is actually what we call vertex form for absolute value functions. So there's a little bit more. You can multiply the x, you can minus something from the x, or add something to the whole group for the absolute value. Now let's go ahead and look at some of these movements. So what we're going to do, it says here use your calculator, but for this one we're going to use Desmos. All right, so Desmos is like the best free thing out there, and I don't think you even need a calculator, a pocket calculator, all that much. I think maybe like if you're taking like some kind of college entrance exam where they only allow the hand calculators, that's the only time I can ever think of them actually being useful. Otherwise, I think Desmos is just like the new thing. So I got the first one already filled out. F of x, if you remember, is just y. So y equals the absolute value sum of x and 2 is the way you would say that. And let's see what happens if we were to graph that. So I'm going to go ahead and move over here. It looks like my zoom is still up from here. So I got the parent function already graphed. All right, so y equals absolute value of x. Again, that's just the simplest way that it can be written. But in the first one, we had plus 2. So what happens if we were to add 2 to the function, so plus 2 to it? So that red function is the parent function, and the blue one is our new function, the one that has been transformed. So in this case here, if I add 2 to both sides, it shifts to the left. Now it's important to know that this one's actually backwards from the way you would think it would go, because if you're thinking that it's going to go right, it's not going to go right, it's going to go left. So the side-to-side movement is inverted. It's backwards from the way you would think it would be. So it's not very intuitive. But at least we can see that now that it has shifted to the left. Now for the problem number 2, they have the same problem, but it is minus 2. And if you look at it here, see, plus 2, minus 2. Plus 2, minus 2. So if you use the minus 2, and again, judging it from the parent function, that's why I left the parent function up there, so you can easily see where it was and where it went. So we can see that it moved to the right 2 spaces. So I'm going to go ahead and fill that in. So shift right 2. Now those are what happened when the number added is on the inside of the absolute value. It shifts side to side, but what happens if you have the numbers on the outside? So this is not in the group of the absolute value, they're on the outside now. So let's go back to the graph. And I'm going to take this out because we don't need this 2 anymore. And I'm going to go ahead and add 2 here. I think the first one was add 2. So let's watch what happens to our blue graph. and it looks like it has shifted upwards. Now it's not changing shape, because if it was changing shape, that would affect the slope or the direction of these lines here. And if I move over this way, you can see that they are running parallel. That means that the slope has not changed, so they are just running side to side. So again, the shape has not changed. It's only the movement. The whole thing has moved over. And let's go ahead and write that in. So this is a shift up. And you could probably guess what's going to happen with this one if adding 2 makes it go up. Now this one is intuitive. It goes the direction you would think that it would go. So -2 would be going down. But let's just verify that on our graph. So I'm going to change this to a minus. And if I do, you can see that now the blue is below the red line, the red function. And now it's below. It's gone down 2 from where it was. So we're right about that. All right, here's where things kind of get a little bit crazy, because we're multiplying it by 2 now. So let's go ahead and multiply it by 2. What do you think is going to happen? All right, just think about that for a second. So multiplying it by 2. Now, what if it was, say, a linear function? What if it was y equals x and y equals 2x? How is the graph different or the same in that one, in that linear function type? So let's go ahead and just look it up. Go back to the graph. So 2 times the absolute value of x. So we're multiplying by 2 now. So go on over to the front, and we're going to put 2 in there, and here it comes. So now you can see what's going on. The graph is kind of narrowing. But what do we call that? Well, we don't call it narrowing. Now, to describe this one, it's a bit of a weird thing. But what you could imagine is, let's say that, okay, I don't have, this is just regular paper, but imagine that we wrote something on here and we are stretching it. So if we pull it, you know, if it was like rubber and I were to pull this thing apart a lot, you would have a very stretched image. And that's exactly what we call this. We call it a stretch, because you're grabbing those lines and you're pulling them apart. Now, I kind of mentioned that they're kind of like line functions. So if I were to kind of hide one side of it, it would look like a line function. So if you think about it, again, y equals 2x. That'd be like your slope, up 2 over 1, up 2 over 1, up 2 over 1. And the red one is up 1 over 1, up 1 over 1. So it's kind of like a slope. It's kind of like a slope, but since we're multiplying the numbers, the x value is going higher, faster. So again, we call this a vertical stretch. And we could probably also say by 2. Now, for the homework, it's not really important to say how much of a factor it's being stretched by, because that's usually not as important. All right, so let's go ahead and go on to number 6. What do you think is going to happen with this one? So if, oh gosh, oh, it's in the back. For this one, it's the very last page for this one. It's kind of written on a little bit of a smaller one, but it's like on the inside cover of the packet. Sorry, I forgot to mention that. I put it in the back so you could easily rip it off if you had to. But I think I'm going to end up using it for the work day of it. Sorry, I should have mentioned that first. Anyway, so let's look at this one here. So I have 1/2 x. So you can think of it kind of like a slope again. Rise 1, run 2, and that's going to kind of cause your line to be shallower, right? So the slope's going to kind of go down a bit. But let's see what it does to the absolute value function. So again, I'm going to go to the home button here. That home button is makes it go back to the center. And instead of, oopsie, there we go. So now it's times by half. And if I were to ignore one side, it'd go up 1 over 2, up 1 over 2, just like that. But this one's a bit of another weird name, because you might be thinking, oh, it's getting pulled sideways. And I've had students say, oh, it's getting pulled sideways, because yeah, that's what I was, when we were talking about things, we were saying pulling. And I'll be honest, when I was in high school, that's kind of what I thought too. When I first heard about this, I thought, oh, that it would be stretching sideways, but it's not. It's not. It's like, if you've ever seen the hydraulic press channel on YouTube, they just basically use a crushing machine, and they just crush all sorts of things. They use a press to crush things. And anytime something is crushed, you know, it kind of gets shorter and stubbier. That's what's happening to this graph. It's still focusing on the up and the down, but it's getting crushed. Yeah, that's fun. There's a lot of interesting things on that channel you wouldn't believe behave that way. You know, you're like, oh, you know, I never actually thought about that. Or, you know, there are some really cool ones like this hollow metal beam, and it kind of like, I don't know, it like weaves itself in a weird thing, pattern. But anyway, yeah, that's pretty neat. Anyway, but again, you're crushing this absolute value line. So from the red line to the blue line, think of it like a marshmallow man, right? If you had a little tiny marshmallow man, or maybe like a gummy bear, if you ever squish the gummy bear, you know, it kind of flattens and gets shorter. And that's exactly what's happening to this. It's getting flattened like a gummy bear. So we call this a compression. I should say a vertical compression, but I'm going to run out of space if I do that. Maybe I'll just put V compression by 2, vertical compression. And now for the last type of transformation. Well, actually, it occurred to me just now that there is one more, but it's not covered here. But anyway, the last one we're going to cover is going to be what happens if you make the x negative. So making the x negative, all right, let's go ahead and go back to our graph. And I'm going to go ahead and erase this. And now that they're both parent functions, they're both the really basic functions. So I'm going to go ahead and push the minus sign on the keyboard. And let me go ahead and take this down so you can see it a little bit easier. Here we go. 3, 2, 1. Ah, I moved the cursor, sorry. 3, 2, 1, boom. So it's going downwards now. It's changed direction. So we call this a reflection. We call it a reflection because it's basically like putting a mirror. If you were to put a mirror like on the bottom of something, you would see that it is kind of upside down. Like if you put a mirror on the floor and somebody is watching you, you would see that the reflection would be upside down. So that's kind of what this is like. It's going the other direction. Now, reflection is kind of a weird name because whenever you think of reflection, you would think of like two things. And if I were to get rid of the original function, so let me just go ahead and I'm going to zero this out. Just there we go. If I were to take this, okay, so I'm only using one function now. So I remove the parent function. So now it doesn't really look like it's reflecting as much. Because usually when you think of a reflection, you think there's two things, but reflections are actually kind of an interesting thing. Like I watched a YouTube video a few weeks ago, and it was, why do mirrors reflect left and right, but they don't inverse up and down? And I thought that was a pretty interesting one because I'm thinking to myself, you know, I just never thought of that. So reflection, and what we'd call this about the x-axis. So a reflection about the x-axis. So again, it's like placing a mirror on the floor. Okay, so just to kind of give you a mental picture, let's imagine there's a pond here, and then you have a buddy standing on the other side of the pond. And there he is looking into the water. And what you would see is you would see him upside down like that. Hey, that's pretty good. So that's kind of how you think of the reflection. Anyway, let's go ahead and go on to the next thing. And this is kind of a chart for what kind of, what changes will cause the transformation. So if we change the formula, now this one you just have to write it in on the packet. I think, yeah, it's kind of just like blank. And if you look at the packet, it kind of looks a little bit smaller. And again, the original purpose of this was that you rip it out. In fact, you know what, go ahead and rip it out because you'll probably need it again later for reference. We were supposed to use this for 2 other assignments, but I don't think we're going to get to both of them this week. So just write this one down. I don't know, maybe, I know not everyone would have a way of copying it, but just write this down on your page. And we have shifting left H units. Now again, the side to side is inverted. It's backwards from the way you would think. So if I add H, you might be thinking, well, if I add H, you know, this way is the plus and this way is the minus. Oops. You know, this way is the plus and this way is the minus. But actually, for these things, it's backwards. So if you shift it if you add a number, you're actually shifting it left towards the negatives. And if you minus something, you would think it would go towards the minus direction, but again, it's backwards from the way you would think. In this case, it would go to the right that many units. And, but at least the outside number, at least the K value is the direction you would think. So up is definitely plus and negative is down. So if I were to fix this chart, it would probably look something like this. If you're talking about the H and this one is the K. But again, side to side, the H value, it's backwards. And if you remember absolute value functions, whatever you put in there is going to become positive. And this is also true with parabolas, which we're not going to get into today, but actually we're coming up on that. But parabolas can be written the same way. And if you move it to the right, that would mean that you are minusing a number. Because again, if you square a number, or if you take the absolute value of it, it will always be positive. So that's kind of how, I don't know if that makes it any easier to remember or understand, but that's kind of why it shifts backwards. Anyway, so we call these stretch and compression, but both of those are called dilations. And earlier I had a comment about can you make them explode? And if you think about it, like when you think about the word explode, it can also mean make something bigger. Like if you, well, I can't really, okay. But it would mean like kind of like zooming in on something. And dilation is kind of a misnomer, I think. It feels like it. And part of this is because when you hear the word dilation in everyday speak, you typically think of something getting bigger. You know, if you've ever gone to the eye doctor, the optometrist, if they're doing an eye exam on you, sometimes they put these like kind of yellowish eye drops in your eyeballs and they feel all fuzzy and numb and everything looks all bright. That's because your eyeballs are dilated. The iris, the black part of your eyeball is opening up. The muscles are relaxing, so you're letting in more light into your eyeballs. And that has the effect of making things brighter, but it also gives the doctor a better chance at looking into the back of your eyeball. But anyway, yeah, so dilation actually does not mean make bigger. It means, it can also mean to shrink it as well. So sometimes people call this vertical compression. They call it a shrink instead. Now, to kind of show what's going to happen with vertical stretch and compression, I'm gonna go back to the chart here, and I'm going to put a number in front of here, but I'm not going to put a number. I'm going to put A here. And what that's going to allow me to do is put a slider there. And what I'm going to do with this is I am going to increase it little by little. So you can see that as I increase it, the stretch is being pulled higher and higher. Okay, but there's also something else I can do, and that is I can also compress it. So as I move the number lower, and now it's reached 1, now it's below 1. As I go down 1, it's getting crushed more and more. So this A value here is less than 1, right? This is 0.4. 0.4 is less than 1. 0.2 is less than 1. These are all numbers less than 1. If it becomes 0, it just becomes a flat line. I can also do the same thing into the negative direction. So negative 0.03 makes it open downwards, and it'll stretch the other way if I keep going. So it kind of looks like a bit of a, ooh, crazy. Anyway, but that's what's going on with this here is when you stretch it, you're pulling it this way. When you're compressing it, you're going that way. But again, that A value, if it's greater than 1, so that'd be like, you know, timesing it by 2 or 3, you're stretching it more. If it is less than 1, like we were looking at the graph, if it's like 0.9 or 0.1 or anywhere in between there, it's going to be making the arms go down or more to the side. So that's what it means here by the A value. And that's the number you're multiplying the X with. And reflections, so a reflection, you saw it on the graph, right? When I moved it into the negatives, it would go down, 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 move into the negatives, and then it would point downwards. So when you make it negative, that's going to cause your graph to flip, to reflect across the x-axis. And like I said, that's kind of like looking at a pond of water, and you see the reflection upside down of somebody standing on the other side. Yeah, and again, dilation doesn't mean necessarily that it gets bigger. It just means that it changes shape. Because you can, dilation also means a shrink. Now, one of them that we did not cover is rotation, and that's spinning a figure. Now, mathematically or algebraically, that's actually kind of tough to do. That's actually pretty tough to do. And for here, we have a question that says, what is the parent function of an absolute value function? So that's easy. You just put these bars on X, and that's again, parent function means the most basic function, like the very bare minimum that you can call it an absolute value. So we're just taking the absolute value of X, nothing else. Now, they want us to look at these and compare them to the parent function. Now you can use Desmos for these. In fact, I think on one of the directions it says use a calculator or something. But anyway, with some of these, you can just sort of follow the reference guide that I showed you, all right? So we are minusing 5 directly from the X. And going back to this chart, minusing something from X is going to cause it to shift right. There we go, shift it to the right 5. And we can go back to that same chart and see what happens if we were to add 9 to the outside. So not directly to the X, but onto the outside. And if we add a number, that's going to cause it to shift up that many units. And again, shift, it just means you move the whole thing. You don't change anything else. You just move where the figure is. And for this one here, again, if you look at the chart, it'll say reflection across the x-axis. And that one's basic. That one almost fits the definition exactly. It fits the definition of what we were talking about. A reflection is, I said x-axis. There we go. That would be the more appropriate way to say that. Now with this one here, we have two things going on with it. We're multiplying x, or I should say the absolute value of x by 3, and we're also minusing 2 from the outside of the x. And so not directly, but on the outside. So you can still use your reference for this. So we know we're going to have a vertical stretch of 3 and a shift down 2. And we can also check ourselves. Let's go to Desmos and times it by 3 and minus 2 and see if that does anything. So I'm going to go back to, well, let me put the parent function back up there. Oh, and to write the absolute value, so if you're graphing this, what you do is you go down to this keypad, and that will allow you to get some more buttons, so you can use your less than, greater than kind of stuff. And there you go. So we have our graph for the parent function. Now I'm going to go to the blue one. That's the one we're changing. And I'm going to go ahead and times it by 3, and that's going to cause the stretch. So you can see that it's, again, pulled upwards. And I'm going to minus 2. So we were right. The graph has been stretched and has gone down 2 units. And sometimes this graph might be a little bit distracting, so you might want to, if it, in this case here, you can get rid of it, or again, bring it back. Oh, now what I just did there was an interesting thing, actually. This is one of the other things that's going to come up, and it just kind of occurred to me. But if you get rid of the absolute value, see how it's a line? It's just an ordinary line. But when I push the absolute value button, keep a look at the 0, 0 place. Keep your eyes there in 3, 2, 1. See, the line didn't change the slope. In fact, it's pretty much the same. It's just that what was in the negative is now positive. So that's what absolute values do, right? They make things positive. So rather than the line continuing into the negatives, it goes back up. And it's not really that important now, but again, we will cover that one later. Now this one seems like we have a lot of stuff to do. We have to multiply it by 1/4. And we have to also add 6 directly to the x. So let's go ahead and go back to the graph and take care of that. So I'm going to go ahead and go here. So 1 divided by 4. And let's see, we have to add directly to the x. And what was the number we had to use? Plus 6. There you go. Now it looks like it might have changed the shape, but that's not really what happened. It's a bit of an illusion. We just took the function and we moved it over to -6. Now again, this is backwards. The adding 6 directly to the x is going to move it into the negative. It's going to move it in the negative direction. And there's our middle point. So now we can see what happened. It's caused a compression and has shifted it to the left. Compression to the left and shift to the left. Oh, come on. I'm not able, oh, I guess so. I thought I wasn't shifting back to this screen. Anyway, vertical, what we said, compression and or let me just save some space and say shift left. Okay, that's probably about as best as I can do. And again, with this one, we can also use the reference, or we can just graph it and see what happened to this one. So we are using a negative number, adding 7 and minusing 2 with it. So plus 7 minus 2 and make the whole thing negative. 7 and minus 2. And we got to make this whole thing negative. Now I should have started from nothing for this one here. Now if I back out a little bit, you can see that it used to be where this red is. And again, it's been reflected. So it's opening downward. And then we move it this way and then move it down. So that's kind of what's going on with it. So yeah, it's been reflected, moved left, and moved down. So reflected, left, and down. I hate that I can't type fast. I injured my finger like 15 years ago now, and now I have very little feeling in my pinky finger on this side, so I have a hard time typing because I can't, in my brain, I can't tell exactly where my finger is, or I can't feel what button I'm touching. So it makes it kind of hard for me to type, especially like the Q, W, S, and E number if I use home key things. Anyway, so there we go. We got all of these put together. Let's go ahead and move on to the next one and talk about vertex form. Now with vertex form, they use this formula here, f of x equals a times the absolute value difference of x and h plus k. And you might have noticed on some of these that h and k are the vertex already. So if you were paying attention to that last graph, I'm going to go back there just for a second, just to kind of show you. Check this number out. We got -7, or actually, sorry, it's not -7. My brain's already in vertex mode. But look at my vertex right here. It's at -7. But I put a 7 in right here. The y value is -2. Now, if you think about this in a line function, because I remember how I kind of showed that they were the same as lines. This is your slope, y equals mx plus b. So it's just like y equals mx plus b in a way, but these numbers on the inside or outside are your vertex, which is where your function turns around. So it's a negative function, so down 1 over 1, down 1 over 1, down 1 over 1. And it starts at -7, -2. Now again, your x value is going to be inverted of the number that it actually is. So if it's +7, the vertex is going to move in the negative direction. So again, that's the important thing with this one here. So this negative right here has to be accounted for. When you take it out, you have to take off the negative, or if it's negative, you have to turn it positive. And a is the slope on the right side, and -a is the slope on the left side. So that might be confusing, and in fact, this whole thing might sound confusing, but actually it's pretty easy once you get the basics. Okay, so I'm gonna kind of guess and say that most of you, after doing just a few of these, are gonna get it pretty easily. So let's practice graphing some vertex forms of these absolute value inequalities. So it says the first thing we gotta do is give the vertex. So again, we're going to have an ordered pair. And our first number is the number opposite of the x. So if it's -2, means it's going to be +2. Y value stays the same, doesn't change. And we're already halfway done. Well, maybe a third of the way done. Over 2 down 4 is where this graph's vertex is. And again, that vertex is the turning point for the graph. Now, just like graphing linear functions, think of this as our y-intercept. This is where the graph begins. Let's see, on which one of these lines was it? Okay, that's not the right line. I think it was this one here. Now, follow the slope. In this case, there's a 1. Remember, there's always a hidden 1 in front of these numbers. So up 1 over 1, up 1 over 1, up 1 over 1. Now, okay, there it is right there. And that's our slope for the right side. And when it said like define the slope for the left side, it said make it negative, right? So invert it. So in this case, our slope is going to be -1. But the thing is, we're running in the direction of the x. So the m is 1, or 1 over 1, and the slope for the left side is 1 over -1. And remember, this is a trick that I've also showed you before, and that is you can move the negative from one side to the other. So what this means is I have a up 1, back 1, up 1, back 1, up 1, back 1, up 1, back 1, and just follow that pattern all the way to the end. And voila, you're done. So let's go ahead and work on some of these. So what's the vertex for this one? You might be thinking, ooh, maybe it's 3, 5. No, it's not 3, 5. Well, we know that the x value, that's the one that's paired directly with the x, which in this case is +5. And we have to make it opposite. But what's the y value though? Well, if there's nothing there, then it means it's a +0. So we have to use the identity property for this one here. So identity property says adding 0 is the same as having nothing done to it. Since there's no numbers being added to the absolute value of x and 5, it's just going to be 0. Anyway, we'll worry about this 3 in just a second. But let's go ahead and mark out our vertex. So back 5, up 0. So in this case, I don't need to change anything just yet. Okay, now I got to worry about this 3. So again, the slope is up 3 over 1 and 3 over -1. So this is easy. If you just had a line up 3 over 1, up 3 over 1, if you're pretty good at linear functions, this is no problem at all for you. And to graph this, all we have to do is match the slope in the other direction. So instead of up 1 over, or up 3 over 1, go up 3, back 1, up 3, back 1, up 3, back 1, and there you go. That was it. So just reverse the slope. And this slope is also -3, up 1. All right, because again, you can switch the negative, but it works. This one works best if you're thinking about going left to right. But since we're starting from the middle, just whichever one helps you graph better. Or again, some people just reverse each of the marks. So if you can imagine a, well, we would call this a line of reflection. So it's basically the same on both sides. They are both going to be the same. So if I'm 1 unit away on this line, I should be 1 unit away on the other side. If I'm 2 units away, and I should be 2 units the other way. And again, well, not again, but we call this the axis of symmetry, meaning that symmetry means that it's the same on both sides. You know, like most humans are symmetrical. All right, I know some biologists are going to be like, oh, but your heart is on the left side more than the right. But for the most part, on the outside, if you were to take a person and kind of mirror their body, it would basically be the same on both sides. Anyway, moving on. Like I said, this gets a little bit easier when you think about it. All right, first thing is let's go ahead and find the vertex for this one here. So vertex, look at our H value. So in this case, if we have to invert that one, so it's opposite. And the X is inverted, but the Y stays the same. So -1, -2 means that our vertex is going to be right there. So it's going to probably look something like that from that point. So let's go ahead and graph it using our, and I forgot which one I was graphing with. So starting from this point, we follow the slopes. So again, it's 2 over 1, because if we want to turn it into a fraction, we put a 1 under it. Up 2 over 1, up 2 over 1, up 2 over 1. Try our best to keep that line nice and straight. And make sure it goes all the way to the edges. There we go. And let's go ahead and work on the other side. And again, all we have to do is match the slope just in the opposite direction. So back 1, up 1, back 1, up 1, back 1, up 1. There we go. Again, see how easy that was? It shouldn't really be that tough. Once you get the vertex, now in this case, again, we're missing this number on the outside. So when I get my ordered pair, it's -6. So I'm going to have to change it to the opposite, which would be 6. And there is nothing on where the K is. So that outside value, the K, it's 0. There's nothing here, so it's 0. So let me go ahead and come on, why is it? No, probably telemarketers asking me who I'm gonna vote for. Like I care. Okay, never mind. I shouldn't have said that because that's gonna start a storm now. No talking about that. Oh, but I get a whole bunch of those. Like they call me all the time being like, oh, who are you gonna vote for? Do you believe in our cause? This politician was, guilty of this. Now they're doing this. Anyway, follow your slope. So we got negative slope, right? So down 1 over 1. Just like that. Now I gotta go back the other way and move over here. So back this way. And that's it. We got it. All right, so let's do some that are a little bit more complicated. These ones are too easy. Let's turn up the difficulty a little bit. All right, so now we have more stuff going on. We got some fractions in there. But again, it's just like slope-intercept form, y equals mx plus b. The only thing is now there's a sideways portion of that function. So let's go ahead and mark out our vertex. So in this case, again, it's the opposite of the inside number. So now it's +1, so it's -1, but again, this number stays the same. So it looks like our vertex is at -1, -1. So that's our vertex. Now we have to follow this like a slope. Up 2 over 3. and up 2 over 3 again. And there we go. Now 2/3 is less than 1. So if you were to turn that into a decimal, it would be 0.6666 if you were to use a calculator. And 0.6 is less than 1, so you're going to have, like, from the parent function, it's going to be a little bit downwards, more downwards. And again, I just have to go back the other direction and do that. So up 2, back 3, up 2, back 3. There we go. Oh, and that's it. We're done with that one also. Let me go ahead and move on to this one. So inside number is going to be 0 because there's nothing in there with the x, right? That'd be x plus 0. But on the outside, we have 7, and that one does not change. And no, there is no such thing as -0. So 0, 7 is up here. Now we have to follow the slope. So down 3 over 4. Down 3 over 4. There you go. And now I have to mirror it this way. So if it kind of looks a little bit off, you know, like this, no, that's not reflected, or that's not reflected. Best thing to do again is just go down 3 over 4 and try to pass that point. There we go. Let's see. So for these ones, again, they're piecewise, and basically it's like a function. It's like there's two functions, but there's directions on where to put them. So I'm going to go ahead and I'm going to just draw an imaginary line because this is the directions. X is less than -1. So imagine that there's like a hidden line here, and that line is telling us where we should put our numbers. And over here I have a line function of 4x plus 2. Okay, so this shouldn't be that tough. 4x plus 2. Start at 2, go up 4 over 1, up 4 over 1. So you end up with something that looks like that. Now for this one here, I'm going to kind of make it a little bit more. There we go. But here's the thing. So you graph it like a regular line, but hold on. This direction is saying x values less than -1. So what we got to do is we got to take this line and shorten it as best we can so that it stops right there. So if the line continued, it would go past there. Now what we got to do for this side is for x values greater than -1. So that means on this side of that line. So go to the vertex, which in this case is -3, 0. So back 3, down 0. So our vertex would be right here. So we'd have a line down 3 over 1, down 3 over 1 would look something like that. And I'd have a second one on this side. That's what the whole thing would look like if I graph this. But it says only if x is greater than or equal to -1. So actually, I don't need that leg. And I don't need this much here either. So let me, where was that line at? All right, so I'm just going to try to mentally take a picture, and it's going to look like that. So we erase everything on that side of the graph, basically. So again, it's just like two functions. It's just like systems of equations, except now there's a direction, a set of directions that tells us this side or that side of the line. So in this case, x is greater than -1. So going back to this first one here, I'm going to say x values, there's nowhere equal to, so I use an open circle. And for this one, I'm going to use a closed circle because we have that mark there. And like I said, don't worry too much about these ones. It's just I'm just going to cover them anyway, but you don't have to worry too much about that. I'm going to go ahead and color code these lines just so it's a little bit easier to follow, maybe. Now, I'm going to go ahead and mark out the areas. So in this case, look at the directions. It says graph this only when x is less than -4. Okay, that's -3, so I got to go a little bit more over. Now, don't draw these lines, or if you do, kind of make them a bit light because you might have to erase them later. So these are the segments. I'm going to have a different graph here, a different graph here, and a different graph here. And I'm just going to use the same rules that we've been using. So this is opening downwards, absolute function at -1 up 5. -1 up 5. And it's going to look like this, down 1 over 1. Something like that. Now, if I were continuing to draw this, it'd look like that. But again, the directions tell us we only want this for values less than -4. So there you go. My line stops right there at 4. Now I'm going to need a green line, because now there's a second line. Now this line kind of looks weird because it doesn't really have anything except 3, but that would be y equals 3. So I'm going to use a line segment and mark out y of 3. And I said I was going to color code it. Move it over here like that. There you go. And again, we only use the y equals 3 line between -4 and +2. So that's the only place we graph it. The line ends between those two spots. Now that line should have been orange. I said I was going to color code it and wasn't even following my own. Okay. Last one is for x is greater than 2, so that's this last area of the graph. It would look something like this. So go to 7 and down like that. That's what it would look like. But we're only going to have to start here, because again, it would go up to 7 like there. 7 would be here. Well, let me just graph it regularly and then I'll trim it later. There we go. And then shorten it so that it crosses here, right there. Now I'm going to go ahead and eliminate my lines that I use just to draw it. And you might be thinking to yourself, when are these ever going to come in handy? And that's a pretty good question. But anyway, I'm going to go ahead and use a filled circle because we have the or equal to here. And remember, a function cannot fail the vertical line test. So I'm going to use an open circle because there is no or equal to here. So if I try to pass a vertical line right here for the vertical line test, it would not touch this orange line. It would only touch the blue line. And the same thing for here as well. You would have a line open here because that's telling you there's nothing there. But since there is an or equal to on this green end, that one's going to be a filled circle. So now we have an area where there are no overlaps. So this is still a function. It's a piecewise function, meaning again that there's different pieces graphed together. Now, okay, so back to what I was saying about, is it useful? Well, yeah, it's useful. Let me ask you if you've ever gone into a store, right? So we all know about like shopping, right? If you buy 1 hot and spicy, it's $1.08. 2 is $2.16. Buying 3 is $3.24. So that's linear. But do stores ever offer special deals like buy 1, get 1 half off? Yeah, they do. And if you look at the graph on those, they would probably look something like this. Or like if you buy a bigger pack, the unit price changes. So like if you go to Bash's and you buy a small pack of hot dogs, it'd be like $4, $3-4. Go to Sam's Club and buy a 60 pack of hot dogs. And if you were to calculate how much each hot dog cost, the price would be different. It would probably be a bit cheaper at Sam's Club to buy the 60 of them because they would rather sell you a lot at once, knowing you'll buy it, right? But anyway, yeah, that piecewise functions are real. They are used quite a lot. And now we're at our last two. Now, the thing that's different about these is the mouth. We're using inequalities, not equations. But you do the same thing. -4, -6. So again, change that x value and keep this y value the same. So let's graph our vertex of -4, -6. Okay, and now we have our slope, which in this case there's nothing there, so it's 1. Up 1 over 1, up 1 over 1. And I guess I'll just leave it green. Make sure I'm going through all those points, just like that. And again, mirror it the other side. There we go. But there's one more thing. We covered graphing inequalities not too long ago. In fact, I'm pretty sure it was this week. Check out which way the mouth is opening. This one is opening away from the y. So using the y on top, so on the very top of the y-axis, there's a little y indicating that it is the y-axis. We have to shade the side opposite of that. So that means we shade everything below the line. So there we go, shaded everything below the line. And that's the only extra step. But again, it's the same as graphing linear inequalities. If you graph a line, exact same thing. So let's go ahead and do the same thing for this one. So let's get the inner, not the inner, vertex. So it's opposite of -5, so that'd be +5 and 4. So that's our vertex. So over 5, up 4. Let me just double, yeah, okay, that's about 5. So our vertex is there and it's a negative, so that means our lines are going to be opening downwards. Move this down. And it looks like right about there. Oh, wait a minute. I got the slope entirely wrong on this one. Not only that, but I got something else totally wrong. We are going to need dashed lines because this one does not have the or equal to. So I'm going to fix that slope down 2 over 1, down 2 over 1, down 2 over 1. There you go. That's much better. And again, dash line because the dash line has no or equal to. So the dash line is kind of saying like, okay, well, this is not a very solid barrier. It's not something you really should go near or be right on it. So down 2, back 1, down 2, back 1, down 2, back 1. There we go. Somehow that doesn't look right. Okay, I guess I'll fix that. I think I just got a little bit too down. I think I went a little bit down lower than I should have. There we go. So anyway, we got that absolute value graphed. Now we just got to shade it. And again, look at the little mouth. It's open towards the y. So that means we shade the side that has the y on it. So we shade the top. So just slightly shade that in with your pencil. And there we go. Now we have our inequality graphed and our vertex stated. So we are done with this one. And I guess that's it for this lesson. Let me go ahead and get back to the screen. Oh no, it looks like, anyway. So anyway, that's it. Let me know if you have any questions. I'll be around for another minute if you want to. But yeah, lesson-wise, that's it. And again, no school tomorrow. So I will see you Monday from here. All right, ignore the Zoom telling you to get on your lesson because there is no lesson tomorrow. Anyway, that's it. Bye-bye for now.
So